because we're going to try, yeah, these are your old notes. This is what we've already done. We're just going to go back through and do a quick review of these to see if we can maybe relieve a few fears and hopefully get some better quiz grades. Yeah, pop quiz today. Whoop, whoop. We love those. All right.
No spoilers.
No, we love those. All right, so here we go. Now remember, we talked about how there is a difference between the electronic geometry and the molecular geometry, okay? Now the electronic geometry is easy. You just add up all of the areas of electron density, and if there's 2 areas of electron density, then it's linear, which just means it would be in a line. If there's 3 areas of electron density, it would be trigonal planar, because tri means 3. If there's 4 areas of electron density, it would be tetrahedral, because tetra means 4. If there are 5 areas of electron density, it would be
Trigonal bipyramidal.
trigonal bipyramidal, because 3 plus 2 is 5. And then if there's 6 areas, this one's the one where it gets a little funky. It's called octahedral because it gives it 8 sides. Okay, so that's why it's called octahedral. Now, this is just, what do I mean by this? Like, let's say if we have NH3. Okay. If I draw NH3, how many areas of electron density are around the nitrogen? 4, right? 1, 2, 3, and then this lone pair of electrons counts as 4. So the electronic geometry of this would be what? Tetrahedral. Do we see that?
Yes.
Okay, because there's 4 areas, so it would be tetrahedral. Now, is that the shape of it?
No.
No, that's just the electronic geometry. Does that make sense? Now, the good news is shape and electronic geometry stays the same for 5 and 6. Okay, so all you have to worry about with 5 things is trigonal bipyramidal. All you have to worry about with 6 things is octahedral. Now, when you get to college, they will probably give you more shapes for 5. Okay, but as far as AP in this class, we're just going to stick with 1. Work for you? Works for me. Good. I'm glad we're there. All right, so does everybody understand how to find electronic geometry? Okay, we don't use it a lot, but I do want you to understand the difference. All right? Then we get to molecular shape, and so we use the VSEPR model for that, which just stands for valence shell pair electron repulsion theory.
Yeah.
Valence shell electron pair repulsion theory. Yeah. And all we're saying is yes, there are 4 areas of electron density there. So yes, we would say it's tetrahedral as far as our electronic geometry, but this lone pair is going to affect some shapes. Okay, so we're going to talk about how it will affect the shapes. So let's talk about this in terms of 3D. Okay, let's talk about this in terms of 3D. So let's start with something easy like CH4. Okay. Let's start with something easy like CH4. Now, if I look, let me switch to webcam right quick. All right, if I look at CH4, okay, can everybody see it? I'm trying to hold it so Hopeful can see it and you can see it. Everybody see it? Okay. If I look at CH4, all right, what do I notice? No matter how I turn it, it's all what? They're all the same distance apart. Okay? That's because all of my electrons are being shared how? Equally. Okay? They're all being shared equally. So we would say all of these bond angles are 109.5 degrees apart. And yes, you need to know bond angles. You won't need to know them for your quiz today, but you're going to need them for tomorrow. So go ahead and start learning them tonight. Okay? Okay.
Okay. Are those the only bond angles there are that we're going to need to know?
We're going to go over it. Okay? So these are all at 109.5. Okay? And notice we have how many bonds going on here? 4. So we would still say this shape is tetrahedral. Okay? Tetrahedral. Everybody see it? Everybody see it? We feel good on it? We feel good on it. Alright. Then, let's say we switch over to, let me get it back on my monitor. We switch it over to ammonia. Now notice, ammonia has a what?
Smaller angle because that belongs there.
There you go. My angle went what? Down. instead of being 109.5, even though the electron geometry would still be what here? Tetrahedral. My bond angle went down because I have a what? Lone pair. So that lone pair causes these hydrogens to be what? Pushed down even further. So now my bond angle is 107 degrees. Okay? Now, is the shape of this still considered tetrahedral? No. Okay? What did we say this shape is?
No, trigonal
Pyramidal. Just trigonal pyramidal.
Oh gosh. Okay, I'm trying to figure out.
Okay, now, why is this trigonal pyramidal? Because how many things are bonded to the nitrogen? Let me take it off monitor. How many things are bonded to the nitrogen? 1, 2, 3. That's where we get the trigonal. But that lone pair causes these 3 things to be what? Pushed down, so it makes it in the shape of a pyramid. Do we see that? So that is trigonal pyramidal. Okay, let's go back to my monitor. Now, we have a water molecule. It has how many lone pairs? 2. What did we notice happened to my bond angle? It went down because now I've got even more what? I've got even more electron repulsion, so it causes these hydrogen molecules to be pushed even further down. Now, without those lone pairs, where would these hydrogens be? In a line, right? They would be linear. But because we added those lone pairs, what did it cause the hydrogens to do? It caused them to bend, so we say the shape of this is bent.
Bit?
Yeah, I know.
That's not even scientific.
I know.
It says that when you cheat.
Okay. All right.
Bit.
Do we see that? Makes sense? All right. Now, the other shapes that we haven't talked about is, oops, did I miss it? Let me find it. I thought it was the very next page.
No, back. Go back. Go back. There you go. Go down.
No,
No, it's not that one.
there's a page after it.
You go for it. I think I saw it at one point.
Isn't it the one
No.
with the
I saw it. It had like bent, linear, and all that stuff on
Oh, here we go.
there. There it is.
All right. So if I have a linear molecule, well, let me find one. I just built one. There we go. If I have something that's linear shaped, it's just in a straight what? Line. So the bond angle, sorry, Hopeful, there it is, right there. Just in a straight line. All right. So if it's just in a line, what's my bond angle going to be?
180.
180 degrees, right? Everybody see that? That makes sense, right? Okay. Now, if it's trigonal planar, okay, that means it would be something like ammonia, except there's no lone pair, so this is just being held what?
Captain.
Flat. Okay, it's being held flat. So if I just have something held flat, what's going to be the angle between all 3 of them? 120. Okay, so trigonal planar would be something like BF3, where since there's no lone pair, there's nothing to repulse it, so it just stays what? Flat. Okay. We already went over tetrahedral. Okay. Now let's talk about trigonal bipyramidal. You got to see this one to be able to appreciate it. Okay. All right, so here's the trigonal bipyramidal one. Okay. Now you've got to hold it. Let me see how I can get it to where it made it easier for me to see. Like that. Okay. Now, if you've got the trigonal bipyramidal, I've got 3 bond angles of 120. Do we see that? 1, 2, 3. And then I've got 2 bond angles of 90 degrees.
You got one.
Yeah, I guess if you went there and there. Does everybody see that though? Oh, there's 3 at 120. And then 2 at 90. Which is why it's called trigonal, 3 at 120, bipyramidal, 2 at 90. Do we see this? Yes.
We have a word bank.
Okay. We have a word bank. No, we can't have a word bank on the AP exam. Okay. All right, and now let's look at the octahedral one. Notice all 6 of these are just at what?
Same.
90 degrees.
Oh, I see the eight
That is the
sides.
one we built.
I see the eight
That
sides. What are you talking about? You haven't seen the eight sides.
Wait, what?
I can't see them. I saw them in this picture up here, but I can't see them. Just I guess this is 1, 2, 3, 4, 5, 6, 7.
It's 2 pyramids stuck on.
So
Yeah,
1, 2, 3, 4.
Look, you see how it's
5,
outlined
6.
right there? It's not that hard.
I don't know. I still can't see it. It's just me though. But does everybody see the angles?
Stop the video. We're going through this.
All right. That's what I need you to see. All right. Let's go back to the monitor. All right. So trigonal bipyramidal has 3 at 120, 2 at 90, and octahedral has 6 at 90. Yes.
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 Now, I can tell you we're gonna need to know this too.
Huh?
We're gonna need like to know this for the test book.
So,
All right. Now let's talk about what if they gave me 3 different drawings, like I3 negative. Okay. So they gave me A, they gave me B, and they gave me C. Now these right here are lone pairs. Okay. All of these are lone pairs. Which one of these drawings, A, B, or C, would be the most stable arrangement for I3 negative?
Wouldn't it be the most
Zeros? I'd say
Huh?
the 90. B.
C. Okay. Now, why is C going to be the most stable?
because
That's
if you
right.
have any,
My electron pairs are what degrees apart here? Between this one and this one, and this one and this one? 90. Okay. Then between this one and this one, they're what? 90. On this one, notice I've got a lone pair going back into the board. Okay. I've got a lone pair going back into the board here, and then I've got a lone pair coming out at me here. That means all of these lone pairs are how far apart? 120. The most stable arrangement is going to get my lone pairs the furthest apart, right? Because remember, we're trying to minimize what? Electron-electron repulsion. Okay. Does that make sense? Do we see that? Yes? Yes. All right, exercise 11 says describe the molecular structure of a water molecule. Well, by now, you should know how to draw this in your sleep. Okay. There's a water molecule. What shape is that going to be? Without the lone pairs, what would it be in?
Linear. So
It would be in a line, but because of those 2 lone pairs, it pushes the hydrogen molecules down and it makes it what? Bent. Okay? What if I asked you for the bond angle between these hydrogens? I think that desk is broke.
yeah.
So,
Yeah.
That could have been bad.
Here. One of you guys, will you take that desk and swap it out with that one?
I got it.
No, make one of the guys help you. That's what they're here for. Oh my Lord, Jim. Thank you,
Gotta make sure
Chance.
you don't
Thank
use
you,
that.
Jim.
Oh my gosh, write those down on there.
It's disgusting.
you just.
All right. Sorry, Holtville, we're having technical issues with the desk. We will be back shortly. Huh? Next week.
That one seems like it's 30.
What y'all doing? What are we doing?
I'd take that one down to meta if it fixed.
Wednesday in here. Review, probably. We're going to do a lab Thursday. That includes you too, Holtville.
Oh gosh, we're still gonna be here Wednesday. It's gonna be awful.
All right. Here we go. So everybody see that's bent? Yes. All right. So let's look at exercise 12. When phosphorus reacts with chlorine gas, the compound phosphorus pentachloride is formed. In the gaseous and liquid states, the substance consists of PCl5 molecules, but in the solid state, it consists of a 1-to-1 mixture of PCl4 positive and PCl6 negative. Predict the geometric structures of PCl5, PCl4 positive, and PCl6 negative. Now, before we can predict shapes, we've got to be able to do what? Draw it. We got to be able to draw it, okay? How many valence electrons does phosphorus have? 5. How many does chlorine have?
7.
7 times
There are
5. So 5 plus 28 is? 5 plus 35. Sorry, y'all. I jumped ahead there. Is 40. Divided by 2 is 20. So I'm going to put phosphorus in the middle. I'm going to show 6 chlorine surrounding it. I've got to put lone pairs on all my chlorines. Now, how do I know that phosphorus can hold 5 of these instead of just 4? It's in the 3rd period or greater, which means it has what orbital? D orbital. Thank you, that it can expand into. All right. So 4, 8, 12, 16, 20. So I know I drew all pairs that I needed to draw. Yes? Okay. And what shape is this going to be? There's 1, 2, 3, 4, 5 of them. Trigonal, bipyramidal.
Yes. And you said it's the number of bonds plus the valence electrons? Or is it? No, it's the number of bonds plus the one pair.
It's just the number of bonds. We're talking about shape now, not talking about electronic geometry. All right, that means how many bond angles are going to be? Try. What are the bond angles going to be for the trigonal part?
120.
120. And what's the bond angle going to be for the bipyramidal part?
90.
Okay, I know that question didn't ask us that. I'm just trying to give you practice. All right, PCl4. How many valence electrons does phosphorus have? 5. How many does chlorine have? 7 times 4. And that positive means I have to do what?
Take away an electron.
Subtract 1. So 5 plus 28 is 33. Minus 1 is 32. 32 divided by 2 is 16. So you should automatically know how I'm going to draw this. Phosphorus goes in the middle with 4 chlorines. I surround them all with their lone pairs. And then I have to put it in brackets. Why am I putting it in brackets? Because it has a charge, so I want to show that positive charge. You don't have to circle it. I'm just circling it so you can see why I did it. I check myself 4, 8, 12, 16 pairs of electrons. And what is the shape of this going to be? Tetrahedral. Which means all of my bond angles are at what?
All at
109.5 degrees. All right. Now we've got PCl6 negative. How many valence electrons does phosphorus have? 5. Chlorine has 7 times 6. And that negative means I have to do what? Add an electron. So 5 plus 42 is 47. Plus 1 is 48. Divided by 2 is 24. So I put phosphorus in the middle. Chlorine, chlorine, chlorine. 4, 5, 6. Then I go back and double check myself. I've got 4, 8, 12, 16, 20, 24. So I know I'm correct. I'm going to also put this in brackets because why? It's negative. And what shape is this going to be? Octahedral.
Okay.
All right, so all of these bond angles would be at
90 degrees.
90 degrees.
It's really not that hard. It's just a little hard.
Yeah.
Is this all
Hmm?
Basically other things.
Yes. We just built them all.
Which was the best.
Okay, I enjoy building molecules. Thank you. All right, we already did the recap, so now let's move on to molecular polarity. Okay, so let's talk about, we've already talked about how do I know if I classify a molecule as polar, that means the electrons aren't what? Shared equally. Okay, if I say that the molecule is nonpolar, that means the electrons are shared equally. Okay, now so let's go with something that's about, so we have what we call a dipole moment. Okay, which is a separation of the charge in a molecule. Okay, which just means I'm going to end up with a negative end of the molecule and I'm going to end up with a positive end of the molecule. Okay, so we already know this because I made you know this last year with water. Remember this? We would draw the water molecule and we would say that the oxygen is slightly what? Negative. And these hydrogens are both slightly what? Positive. Why?
Because he's got that one pair, so he's
Because oxygen is more what? Electronegative, which means oxygen is pulling the electrons in towards itself, right? Yes. Okay. So that gives it a slightly negative and a slightly positive charge. Okay. So we would show this by drawing an arrow towards the end that's negative. Which end is negative? Oxygen. Okay, and then we put a plus end on the side that is positive. Now, why did I draw that in one arrow and not two? Because you've got to remember, you're thinking of this molecule, right? You're thinking of this molecule as it would be in its 3D state. Okay, so we're saying all of the negative charge is going up towards the oxygen, and where's it being pulled from? These hydrogens on the bottom. Do you see this? It's just going straight up. Got that? Yes. Yes. Okay. All right. So, we're going to skip ahead for just a second. How come this is nonpolar?
Because he's got 1, 2, 3, 4. He's got wait.
Well, I know
Cancel each
that
other out.
Because carbon can't have
pairs.
Carbon
Okay.
can't have one pair.
This carbon doesn't have any what? Lone pairs. And are the oxygens on both sides distributing the charge evenly?
Absolutely.
Yes. So we say this molecule is nonpolar because the dipole moments cancel each other out. Okay. Now, I know what we're thinking. Well, how come it didn't cancel each other out in oxygen? Because don't I have two hydrogens here that are equally on both sides?
Would you have one person on?
But I've got lone pairs on the oxygens, which establish a strong negative pole.
So 4. Yeah.
Okay? Whereas if we look at ammonia, polar or nonpolar?
Polar.
Polar. Okay? We're going up towards nitrogen, leaving these positive hydrogens at the bottom. Okay? Why? Because ammonia has what? That lone pair, which is establishing a strong negative pole.
So on the little oxygen carbon. So since carbon doesn't have lone pairs, so it doesn't it makes it nonpolar.
Since carbon doesn't have any lone pairs and the charge is distributed evenly between here and here, it causes, even though these oxygens are pulling more electrons, and they are, because oxygen's more electronegative than carbon, so it just can't help it. I mean, oxygen's gonna pull it more because it's doing it evenly. And notice this is very symmetrical. It's linear, right? If I built this molecule, it would be in a straight line. Would this be in a straight line? No. Would this be in a straight line? No. Okay? So since it's pulling it evenly, the molecule is nonpolar because they're being canceled because they're happening evenly. Here, this lone pair of electrons and these two lone pairs of electrons on oxygen is keeping the charge from being distributed evenly. It's giving me a really strong pole and weak poles.
Thank you.
No problem. Okay. So, let's look at CH4. Polar or non-polar? Non-polar. Why is this non-polar? It doesn't have any lone pairs, and all of this charge is distributed how? Equally.
So basically, if it's carbon, it's gonna be non-polar. Yes.
There it is. That's nice.
Polar or non-polar?
Polar.
Polar. How do I know this is going to be polar?
Because it's chlorine soluble.
Because chlorine is more electronegative. So all of these hydrogens down here are going to be more what?
Drawn towards the
More positive. Notice I draw the line to make that look almost like a what? A plus. Okay? And I draw the arrow towards where all the oxygens are being hogged. Not the oxygens, electrons are being hogged.
Okay, just kidding.
Does that make sense? Okay. All right, let's do a couple of examples and then we can call it a day. For each of the following molecules, show the direction of the bond polarity and indicate which ones have a dipole moment. So the first one is HCl. Okay, that's how we draw HCl.
That would be
Is this going to be polar or non-polar? Polar. Okay, who's hogging the electrons here? Chlorine, because chlorine's more electronegative, so I draw an arrow towards the chlorine, and I show where the hydrogen end is going to be the end that's slightly positive. Do we see that? Yes? All right. Cl to Cl. Polar or non-polar? Non-polar. How do I know that's going to be non-polar?
It's the same thing.
The electrons are being shared equally. Okay. SO3. I'm just going to draw these out because y'all should know how to draw them by now. Right?
Yeah.
Okay, and it tells me this is a planar molecule, which means I don't have any what? Lone pairs, which means one of these is a double bond. Because if I had a double bond on sulfur, would it be a planar molecule? No. Okay. It is nonpolar. How do I know it's nonpolar?
Not sure.
Okay, because all of the electrons are spaced evenly around, and that means they're pulling the electrons evenly, so therefore I don't get a dipole moment. Even though there's a double bond there, okay? Don't confuse that with the oxygen is pulling any more or any less electrons. Because remember, we could also draw all the resonance structures for this, and the double bond could be here, or we could draw it where the double bond is there. Remember? Does that make sense?
Okay, so how did you know you knew double bond?
Because it told me it was a planar molecule. So if I did it with a long, like if I only have 3 oxygens, which means sulfur is only making 6 electrons here. 3 bonds, 6 electrons. So to satisfy the octet rule, because we've got to satisfy the octet rule every time, okay, unless it's boron, okay, then I would have to put that lone pair there. Well, that lone pair would cause these oxygens to be pushed down. So it wouldn't make it planar anymore, it would make it trigonal pyramidal. Does that make sense? So because they told me it was planar, I knew I had to draw it without any lone pairs on that sulfur. Okay. All right, CH4, we already did that one. Polar, non-polar? Non-polar. And then H2S. Polar. Does this make sense? We're good?
It makes sense now. And then,
This actually, is it on your quiz today? It is, but it's an easy question. You'll be fine. Huh?
We got a quiz there. Good luck reading it.
All right. Exercise 13, it asks you to draw xenon tetrafluoride. Okay. Now I'm going to draw it for you right quick, and then I'm going to help you answer this question because I don't think. Now I'm going to be wrong, so if you see this on the AP exam, just know I was wrong, and you should know the answer to that. Okay. And then xenon has 2 lone pairs on it. Okay. I did draw this the other day. Now, I'll go ahead and tell you the shape of this, because I don't make you know this, is square planar. So from the shape of that,
You're right, so cute.
So because of the shape of that, just from looking at the name of that shape, do you think this is polar or nonpolar? I believe it would be nonpolar too. Now, why do you think, just from looking at the name, it would be nonpolar?
It's where it's square.
Because it's square and it's what? Planar. Which means it lays flat, which means everything has to be what? Evenly spaced apart. Okay? Now, why is that? Because notice, we want the lone pairs to be what? As far apart as possible, right? So in this case, it would be like if I took this molecule, okay, and I pretended like these are just 2 lone pairs. I put them as far apart as possible and then just smushed it flat. So I cancel out all of the dipole moments because everything, including the electrons, are spaced as far apart as possible. Okay? And then exercise 14 says predict the molecular structure of a carbon dioxide molecule. Is it expected to have a dipole moment? This is a carbon dioxide molecule. It has a lone pair of electrons, and if this was on the AP exam, I would go ahead and put a box around this, and I would draw the resonance structure. Why am I drawing the resonance structure? There you go, because I need to show both ways to draw it. Okay? Is this going to have a dipole moment? What's your first clue that this is going to have a dipole moment? That lone pair. That lone pair is your first clue that there's going to be a dipole moment. Okay. Yes? Yes. All right. Quick review. What time's the bell ring for this class? All right. So I'm going to wrap this up in 5 minutes so you have at least 10 minutes to take your quiz. Okay? All right. So everybody hang tight with me. Now, I want you to star this page because you should study this page because you can get a lot of multiple choice from this page, multiple choice points from this page, including that section on metallic bonding at the bottom. Because we focused on ionic, we focused on covalent. This is the first time we're going to talk about metallic. But it's really easy to sum up in literally that one little few bullet points. But there are questions about metallic bonding on your test. Okay, we're clear? We're clear. All right, ionic bonding. The easiest way to know if something is an ionic bonding is you have a metal to a nonmetal, or you have a positive ion bonded to a negative ion. Okay? Because that is what makes something ionic, is that electrostatic attraction between the positive and the negative ions. Okay? Remember, when they bond, they form a crystal lattice structure. So that makes them solid at room temperature. Because of this lattice, we're not going to count up all the sodium and all the chloride ions that make up that lattice. So we just write them in the simplest ratio of elements. Like NaCl, we're only showing 1 sodium and 1 chloride. But in a salt crystal, is there 1 sodium and 1 chloride? No, there's millions of them, but we're just not going to write it down. Because they have such a strong attraction, we know their melting point is going to be really high. And we know that they are good conductors of electricity only when they're melted or dissolved. Why is it only when they're melted or dissolved that they're a good conductor of electricity?
more space.
That's when they what? Break apart into their separate what? Ions, right? Only when I melt them or dissolve them, okay? When it's in a salt crystal, it's just NaCl bonded together. Is it going to conduct electricity? No, but when I melt it in water, it goes to Na positive and Cl negative. Now can I conduct electricity? Yes, because I've got positive and negative ions. We see that?
So we like a light bulb, salt one?
Carefully. AKA, don't try that at home.
Sweet.
Yeah, electricity and water don't generally mix very well, you know, unless you got the proper equipment to do so. So, all right. Covalent bonds. This is when I have a non-metal bonded to a non-metal. Okay. So ionic is metal to non-metal. Covalent is non-metal to non-metal. This should be a review from last year. Yes. Okay. We share electrons in a covalent bond. We give their formulas in a true ratio. They can exist in any state of matter. They melt at lower temperatures because the bond is not as strong as an ionic. And they are not conductors of electricity because there are no charges, no ion charges there. Metallic. Here's the one we haven't talked about. So this is the one. We did talk about it last year, though. How do we say metals bond together? You may remember from last year our saying for it. Because there's a sea of delocalized electrons moving around. So the electrons are constantly flowing back and forth, back and forth, back and forth, so it holds them together, okay? For instance, like if you're wearing any jewelry, ladies, okay, is that just one atom of gold in your ring? No, it's millions of atoms of gold, okay? It's a metallic bond. The metal's bonded to a metal, okay? Why? It's an attraction between the metal ions and the surrounding electrons. Because remember, let's take copper, okay, Cu. If light hits the metal surface at enough frequency, what did we say happens? The photoelectric effect. There you go. It shoots off a what? Electron. So when that electron shoots off, that copper becomes what? I get a Cu positive ion, which means all the other negative electrons that are floating around, remember it's the sea of electrons, are going to be what? Attracted to that positive copper. So then it just causes a little clump of copper. Does that make sense? So that's why we have metal that's in sheets or clumps or rocks or in rings and not just floating around in air. Does that make sense? Of course it does. Okay? But we write their formulas as neutral. Like when I write copper, do I write a Cu positive and show electrons all around it? No, I just write it as Cu. Okay? They are solids at room temperature. They have a range of melting points. And they are great conductors of electricity because the electrons are all free to move around. I did that in exactly 5 minutes. Yeah. All right, take out a piece of paper. You too, Hopeful. Take out a piece of paper. All right. And here is your quiz. You do not have to write the question. All you have to do is write the answer. You cannot use your notes.
What if we get points for the right question?
Huh?
Will we get points for that?
No.
Yeah.
Okay.
So I don't know how to write the answers. Mine's gonna be solid.
All right, you've got the remainder of the class period to take this quiz.